Okay, so far we've been talking about protons, neutrons, and electrons, and we said the protons and the neutrons are in the nucleus, and they're surrounded by the electrons in the outer cloud. So we are leading ourselves to where the electrons are. The reason we care about the electrons so much is they are going to be involved in the chemical bonding. So it is very important for us to understand the properties of the electrons and why they move, why they transfer, why they get shared, etc. And a lot of discoveries went to that. And we know that electrons are moving, and they're moving really, really fast. So today's lesson is about how we kind of know where the electrons are. So the scientists actually studied the properties of light, and in lab we'll do a lab where we will excite some elements or compounds, and they will give off the property of light, and we'll be able to look at their spectrum and determine the element that we're looking at. So we're going to begin, and so we're again talking about where the electrons are. So a lot of you in high school, hopefully maybe not in high school, but in middle school, learned the Bohr model. And you're looking at the Bohr model of neon. And so the Bohr model is a very simplistic model. Niels Bohr originally said that the electrons are in nice little energy levels, and they're going around kind of like orbiting a sun, with the sun being the nucleus there. And he put 2 electrons there, and there were 8 electrons. And a lot of you drew Bohr models in probably middle school. You still see it in the biology textbooks. But we now know it's much more complicated than that. And Niels Bohr actually knew it was much more complicated than that as well. And he went on and worked with the other scientists for the quantum mechanical model, which is the model we now use for the atoms. So Niels Bohr didn't just leave it at that. We still use this biology textbooks, middle school textbooks, because it's easier for our brain to kind of understand. So these are the energy levels, and I'm still going to be using that term energy level, but I would like you to understand that energy level really is just kind of a distance from the nucleus. And so we're going to have first energy level, which will be closest to the nucleus, and then second energy level would be out a little further, third energy level, etc. And so that leads us to, we're not going to do all the quantum numbers because we're not learning quantum chemistry. We're going to just hit a little bit. So we're going to learn the main one, which is known as the principal quantum number, and it is just depicted with the letter N in formulas, and that basically represents the energy level we were referring to. So N equals 1 would be first energy level, N2 second energy level, etc. And we will start talking about how the periodic table are arranged, but the energy level is the period number. Basically, the period number is just the row number. And currently, the periodic table has 7 rows. So currently, there are 7 energy levels. So I say currently because they've actually filled up the 7th row, and probably very soon you're going to see an 8th period, an 8th energy level being produced. So we'll see how that goes in the near future. So what we're going to first learn to do, so we're going to learn some very basic calculations today, a little bit of physicsy stuff. We're going to learn how many electrons could we put in each energy level if they were to completely fill up. And so on your test, I do have some questions, and I'll say how many can the 5th energy level, how many can the 4th energy level hold? And so the formula is the maximum number of electrons we can hold is 2n squared. And so if you've learned PEMDAS, you always do the exponent first. So you're going to raise it to the power and then multiply it by 2. We were always taught, please excuse my dear Aunt Sally, but a lot of you learned PEMDAS. So I have the first 7 energy levels here because we don't have 8 yet. And so we're just going to calculate how many electrons each energy level can hold. And so, I don't know what happened there. I must have clicked something, sorry. There we go. Sometimes always happens. All right, so if we were doing the first energy level, we're going to simply put 2, but it's going to be the n is going to be replaced with the energy level. So you always square it first. So 1 squared is just 1, and then you multiply it by 2. And so the first energy level can hold 2 electrons. Neil Bohr said that, 2 electrons, right? So the second energy level, that's not that 2, that's this 2 in the parentheses there. You square it first. So 2 squared is 4 times 2 and is 8. So the second energy level can hold 8 electrons. A lot of you learned 2, 8, and then you learned 8. That's actually not true. It's not 8 for this third energy level. The third energy level, that would be 9 times 2 is 18. If you were thinking like, I remember something about 2, 8, and 8, there is something about 2, 8, and 8, and we're going to learn that in our next lesson. So you weren't lied to, you just weren't given the whole story unless you've already learned the principal mechanical model there. So the fourth energy level, of course, I'm going to not write it out anymore. So 4 squared is 16. 16 times 2 is 32. 5 squared is 25. 25 times 2 is 50. 6 squared is 36. 36 times 2 is 72. 7 squared is 49. 49 times 2 is 98. So I would like you to be able to use this formula depending on, and I won't give you like 8th or 9th energy level because we don't have any atoms with 8th or 9th energy level yet. But what we're going to learn is in middle school you were probably taught that the first energy level fills up and then it goes on to the second energy level, and then it completely fills up and it goes on to the third energy level, and it completely fills up and it goes on to the fourth energy level. That's not true either. So, because we don't have any atoms that have, if you add all those together, way over 200 and something, probably over 300, we don't have any atoms that have that many electrons. So there's some weird things that goes on, and that's what we're going to be talking about in our next lesson. So for now, I just need you to be able to go 2n squared and to be able to figure out, if I say, how many electrons what's the maximum number of electrons the 7th energy level could hold, you would be able to do that. And there are a couple of those on your test. All right, on we go. So there's Neil Bohr. And so again, he pictured those electrons going around the nucleus. But what he learned as he studied more, and he did learn that they weren't nice and little circles that was going on. We did have some craziness going on with the atoms. But the electrons got excited. They would actually jump from the quantum area where they were, such as it's the second energy level. They could jump out to like the fourth energy level. That was so he had to get excited. The way atoms get excited, or way electrons get excited, is by sending some electricity through them or some sort of energy, fire, etc. So there's this jumping that goes on. So they'll jump out to a bigger energy level, and then when they jump out, they actually fall back down. It was this process that they learned. That is how light was created, or is created. So light is what was studied to help us with the new model that we're going to learn, which is called the quantum mechanical model. And properties of light are part of what we call electromagnetic radiation. So there's a big argument is whether light is a particle or if it's a wave. Technically it's both, but we're not going to get into that. Some of you are going into engineering, etc., so you'll go further into that. Some of you may major in physics, so you'll go further into that. So the electromagnetic, you've probably all have seen the electromagnetic scale before, but some other things that are part of electromagnetic radiation. So all these things follow the same rules. So if you study physics, because I know a lot of you are biology majors and you're going to have to say physics, you'll learn about light and radio waves, etc. So gamma rays, X-rays, visible light, which is what we're going to be looking at, radio waves, microwaves, they all are a form of electromagnetic radiation. and they actually study the properties of light to help us determine where the electrons are. I do apologize if you hear my dog in the background. All right, so as they learned about visible light, if you've ever looked at visible light through a spectrum, I do apologize if you can hear my dog. You can actually see the colors of the rainbow. Okay, our brains can't comprehend the different waves, so it all puts it all together as white light. But if we look through a prism or a rain droplet, it will bend it so that our brain can actually see them individuals, and so that's where you get the colors of the rainbow. So white light actually will split up and make the Roy G. Biv. And so I would like you to know the colors of the rainbow, which is the colors of visible light, white light. So red, orange, yellow, green, blue, indigo, and violet. But honestly, true, do you know how Pluto is no longer a planet? It's now called a dwarf planet. And, they've actually kicked indigo out of the color of the rainbow. So they said it was too close to blue and violet. So it's just Roy G. Biv now, so just B and V. So I still say indigo and violet just because that's what I always was taught. But so Roy G. Biv, the colors of white light is so if we could see. And so in lab we may look at our spectrums and we may look up at the white light with them and we will see the Roy G. Biv being produced. So here's the electromagnetic spectrum that I was referring to. So some of you have seen this before. So you've got radio waves here and you've got gamma rays here. So maybe you could just even tell the ones that might be harmful to us. Can you see that these over here are probably the ones that are harmful? There's more of them. They're more frequent. Okay, they're more frequent. Over here, they're not as frequent. They're longer. This is called a wavelength. From the top of this wave to the top of this wave is called a wavelength. Or from the bottom of this wave to the bottom of this wave. This is the crest and this is the trough. But this is a wavelength from there to there or there to there. That's one wavelength. So you can see radio waves have very long wavelengths and gamma rays have very short wavelengths. The visible light, this is what we can see with our eyes. We can't see infrared, we can't see ultraviolet light, and so the UV lights and stuff is what starts damaging our cells because they get more frequent there. So if you're looking at that, we're going to be talking about some properties. We're going to learn how to calculate wavelength and frequency and energy. Those are the things that we're going to be looking at. On here, the ones that have the smallest wavelength, or shortest wavelength I should say, those are going to be the gamma rays. So they're very close together. So the shorter the wavelength, the more frequent they are. Can you see that? They're very frequent over here. The longer the wavelength, the longer the distance over here, then these are going to be less frequent. So less frequent, more frequent. So if we're looking at visible light, can you see that red would be less frequent and the violet would be more frequent? It has a smaller wavelength. You can even see it about 400 nanometers, about 700 nanometers there. So these are longer and these are shorter and these are getting more frequent. And if we then put this on a terms of energy, if we looked at the whole spectrum, which one looks like it has more energy? The whole spectrum. Gamma has so much more energy than, just think of like a slinky or something. This would be compressed and let it go. So this one would have a lot more energy with it, which is why it's harmful to your cells, because it bombards your cells and can cause cancer. X-rays, ultraviolet light, etc. Okay, radio waves don't hurt our cells because they're less frequent and less energy involved with them. Okay, so visible light doesn't hurt us either. Same reasoning. So we're going to get more energy over here, less energy over here. So if we think in terms of light, the color that has the most energy is actually the violet color. A lot of students want to say red, when you look at, they're like, oh, red, because I think fire has lots of energy. But it's actually the blue flame is actually a hotter flame than the orangey flame. So in lab, we're going to always want the bluer flame for the higher energy purposes for that. Okay? So here's what happens and how those colors get evolve there. So we've got a hydrogen atom here, and hydrogen only has one electron, so it's easier to show a picture with one hydrogen. And so this we say is a ground state, hydrogen, and we're going to be looking in the tube, and we'll look at hydrogen gas. So in ground state, gases usually are clear. There's no color to them whatsoever. Hydrogen gas, we have it everywhere. Okay, but we can excite the hydrogen atom or the electron. Make it click. And so when we excite it through, and in lab we're going to put electricity through it, it will jump, and it can jump out to the second energy level. It might go out to the fourth energy level. It may go out to the fifth or sixth energy level. It just depends. And then it's going to come back down. So eventually it'll jump out. It's going to go to different energy levels, and then it will be falling back down. When it's jumping out, it's called excited. It gets excited because we've shot electricity through it. Just like if I were to shoot you with electricity, you would jump, right? So the electrons jump from their ground state, and then they fall back down. And depending on the distance that they fall, they're going to emit what's called a photon. This is a vocabulary word you need to know for lab, is a bundle of light energy. A photon is a bundle of light energy. And what happens, it's going to emit this energy. So basically a wave particle is given off, and depending on this wavelength, is going to be what color we're going to start to see. So, and it depends on where it jumps from is which particle. And so that's kind of cool that we know all that. So white light makes Roy G. Biv, but each gas, not just gas, each element has its own spectrum, we say. It makes a different pattern depending on how many electrons are moving and how far they're falling back down. So it'll make a different pattern for you. So we're going to be looking in lab, not through a prism. We're going to be looking at through a spectroscope, and we're going to be looking at the different patterns that each gas will make. And each gas is different. And that's how we can identify certain elements. So for instance, hopefully you know that our sun is a star, and our star is made up of two gases, hydrogen and helium. How do we know that? How in the world do we know that our sun is made of hydrogen and helium? Well, we look at it through a much fancier spectroscope than you guys are going to be looking at in lab, and it gives off the pattern of hydrogen and helium. So that's how we know. We've never sent anything to the sun, it would burn up. So that's how we know, and depending on the pattern. So it's called its atomic spectrum, and each element has its own, and they all look different from one another. So in lab, we'll be looking at different elements, and we'll be drawing these spectrums. This is what you're going to be drawing in lab when we do the spectrum lab, which is our lab number 3. And each element's going to be unique. So that gets us to our calculations that we're going to do. We already said that wavelength is the distance from the two waves, either from the top to the top, which is the crest to crest, or from the bottom to the bottom, which is the trough to the trough. Okay, and that's measured in the units of meters. actually our little instruments in lab actually measure them in nanometers because they're so small. So we're going to have to do some converting from nanometers to meters, and we've been working on dimension analysis, and nano means 9, so there are 1 times 10 to the 9th nanometers in 1 meter. Thing's not wanting to turn. There we go. That's just showing from crest to crest for a wavelength. I meant to show you. Do you see this weird symbol? That's called lambda, and it's basically, it looks like an upside down. It's Greek letter. That is for wavelength. We use L for length, and so to differentiate regular length from a wavelength, they went to the Greek alphabet. So that's lambda. That's an L in the Greek alphabet. So it looks like an upside down W. So first thing we're going to do is just do a simple converting. I am going to require that you show this in on your test and also in lab. So let's do that. Let me get to a color we can see. So I do want you to show it, and I do want to show you to show it in a dimension analysis table. And the reason I'm making you do that is because I'm trying to set you up for when we do grams to moles and all that stuff. So I know a lot of you can already get the answer. I don't care about the answer. It's this setup that I care about. And because meters is one of our base units, we can actually go directly from nanometers to meters. We're going to bring nanometers down. We're going to bring meters to the top. In 1 meter, there is 1 times 10 to the 9th nanometers. So this will cancel. So I end up dividing 755 times 10 to the 9th, 1 times 10 to the 9th. So you're going to get 7.55 times 10 to the negative 7th of a meter. So I'm wanting you to show that on your test and in lab for your lab notebook. Okay? All right. That's just a converting. About to need it. And then frequency is how many waves pass a given point per second. Okay, so it's how many waves are per second. And so the unit for that is called per second, or seconds to the negative 1, for those of you that have learned that in your math classes, or it's called hertz. So hertz is the unit of per second. So we just put Hz for hertz. So frequency is measured in hertz, or per second, or seconds to the negative 1. And this is what I was showing a while ago. They're inversely related. So the longer the wavelength, the less frequency there are. So a long wavelength is a low frequency, and a short wavelength would have a high frequency. And this would have less energy, and this would have more energy. And that's just that again to show you that. Okay. So, just like we had that mountains over Death Valley, we have a little formula for this. So, let's see what color I want to use. Maybe we can see red. I don't know if we can see red. Maybe we can see that. There we go. All right, C is a constant. This is the speed of light. And that is 3 times 10 to the 8th meters per second. That is the speed of light. It's a constant. Memorize it. Okay? There's that weird looking lambda guy, and that is wavelength. Wavelength has to be measured in the units of meters. And the reason it must be in meters is because this is meters per second. That's why. And F is frequency. Frequency is a per second is what it is. It's waves per second is truly what it is. So we say seconds to the -1, or we put hertz, HZ. I would actually prefer hertz, but I'm okay with seconds to the -1. You could actually put per second, but a lot of people will put just seconds and that messes things up. Okay, it's a per second because this is meters per second. Okay, and of course there's a dot in between there. So just like when we use the density one, you cover what you're looking for and that becomes your formula. So if you're looking for wavelength, you can take the speed of light, divide by the frequency. If you're looking for frequency, you would take the speed of light and divide by the wavelength in meters. So very simple that. We won't be looking for speed of light because it's a constant, 3 times 10 to the 8th. So you wouldn't be looking for the speed of light. Okay, so let's do that one. Okay, so it's wanting frequency. So frequency, I would like you always write your formula, is the speed of light divided by the wavelength. The wavelength needs to be in meters. Do you see how this is in nanometers? So that's going to need to be converted. So we would need to convert this, and the reason is this is 3 times 10 to the 8th meters per second. So I'm going to need it to be in meters so that it would cancel out so I can end up with per second. So I do want you to show that. Nanometers, again, I know some of you can do it in your head, but we're trying to practice this. So bring nanometers down, meters to the top. In 1 meter, there's 1 times 10 to the 9th, and we would get 7. We'll go ahead with 3 sig digs times 10 to the -7th of a meter. So we are going to divide. Make sure that you can put this in your calculator correctly. If you are not getting the answer that I am getting, don't just trust me, because you're going to mess it up on the test and you're going to lose points, or you're going to mess it up on Chem 101 and lose points. So make sure that you're getting the answer that I'm getting here, which is we're going to do 3 sig digs because there's 3 sig digs there. 4.29 times 10 to the 14th. Can you see those meters canceling out and I'm left with a per second? Per second is the same thing as a hertz, which makes sense because that's your frequency. All right, super friendly. They're just some physics type problems. I'm supposed to teach you some of the calculations that are involved with light. Okay, so then we've already made that correlation to the longer the wavelength, the less energy. The higher, the more energy. And we get different amounts of energy depending on which wavelength is given off during the photon being released. So we're going to get energy coming here from the second to the third, or the third, if it was the third, to the second. Some of the harder problems I decided not to do this semester, so we're just going to stay with the simple ones. And so we're going to learn how to calculate energy, and I'm going to say this because we'll do some more energy problems later. But energy is always measured in the units of joules, some sort of joules, either kilojoules or joules. We're going to stay with joules for this one. So energy is either, well, let me go ahead and click some more. Okay, so we've got 2 formulas for energy. Energy is something called Planck's constant. I will give you this, 6.63 times 10 to the negative. Mr. Planck did lots of studying between frequency and wavelength, and he found these proportions, and he developed that constant. We'll just leave it at that. And that's joules times seconds is the unit on that. We've already seen frequency, so that is our F, which is hertz or per second. So it's this formula, or it's this one, which is Planck's constant times the speed of light divided by the wavelength. This C divided by lambda is just been substituted for F. So if y'all understand substitution in math, since we didn't know F, we just substitute C divided by. So these are the same formula. I will give you those formulas on the test, so you don't need to memorize them. And I will give you Planck's constant as well. I just need you to be able to calculate it. All right, so how much energy? So I'm looking for E, and I've been given wavelength. So wavelength is that weird looking guy. I went ahead and gave it to you in meters. You're welcome. So it's already in meters. It does need to always be in meters when you're working with these problems. So if it's in nanometers, you'll need to change it. Because it's wavelength, I would want to use the formula that had the wavelength in it, which is h times c divided by the wavelength. Okay? So the h is a constant, 6.63 times 10 to the negative 34th joules times seconds. And our speed of light, which is the c, times 10 to the 8th meters per second, divided by the wavelength, which is 4.20 times 10 to the negative 5th meters. You don't need parentheses around that. Well, technically, I would tell you to always put parentheses on scientific notation in your calculator. Those of you who want me to teach you how to use the E key in your calculator, I would love to do that for you. All right, if you'll look, we can crunch those numbers. You should be getting 4.74 times 10 to the negative 21. That is not much energy, but it is light, so we don't get huge amounts from the light. So let's look at the units canceling. Can you see that this seconds would cancel with that seconds, and that meters would cancel with that meters, and you would be left with joules. That's where that unit comes in. And so that is energy. You'll be using that calculation in lab as well. So that is the light calculations. It is all of these calculations and these crunching of numbers that led us to the quantum mechanical model, which is where we're heading in our study. So we're going to learn electron configuration next unit, or next, not next unit, this unit, but next lesson. So we had to just do some of the physicsy stuff. We don't go near in depth as Schrodinger with his calculations did, but just enough to get us seeing a little bit of physics, because light is a physics concept, but it did lead us to the discovery of the electron. And if you enjoy electricity, then you should enjoy electrons, because it's all of that, understanding all those properties while you have that smartphone and everything else. All right, that's all we got for you today. So I'll see you in class.